As recently as 50 years ago, before there was a digital clock built into every appliance in your house, your stove, your oven, your dishwasher, your coffee maker, your microwave, your TV set, even your telephone, before a lot of those things even existed, if you wanted to be on time for something, you had to have one of these, a real live mechanical clock. It doesn't take electricity, it never needs batteries, and it didn't come with an incomprehensible instruction booklet just to be able to use it. No, you just raise those weights every day, point the hands to the correct time, and start the pendulum swinging. Ah, those weights are interesting, aren't they? A gravitational battery. How come we don't do that anymore? This is why. This battery here contains the same amount of energy as raising one of those weights all the way 1,850 times.
Clocks like this work because they contain an extraordinary piece of science and engineering called an escapement. This mechanism does two incredible things. First, the escapement allows this spiky-looking wheel to rotate by only one notch at a time. The clock's pendulum is connected to the escapement and ensures that each step of the wheel takes exactly the same amount of time. The pendulum's length is adjusted so that it makes as close as possible to 4,104 swings per hour, or once every 0.877193 seconds. In 36 swings of the pendulum, the escape wheel makes a complete revolution. In 114 rotations of the escape wheel, the minute hand makes a complete rotation, indicating exactly 1 hour.
The second thing that the escapement does is it gives the pendulum a perfectly timed little kick to keep it swinging exactly that amplitude. Its ability to do these two jobs with incredible precision is the result of hundreds of years of research and development. Technical colleges in Switzerland used to have a department of escapements with specialist degrees in the field.
Some of the brightest minds in science contributed to the escapement, beginning with the first true scientist in the modern sense, Galileo. It occurred to him that a pendulum could be used to keep time while watching the chandeliers in the Cathedral of Pisa swaying overhead with remarkable regularity. A bit later, in 1657, Christian Huygens made crucial improvements to the design and is credited with building the first really useful pendulum clock. He also discovered the rings of Saturn, the equation for centripetal force, polarized light, and he invented science fiction.
Ach, das ist mir wurscht.
Robert Hooke and John Harrison and many others made subsequent critical refinements to mechanical timekeeping.
This particular clock was made in Germany in the 1970s at the very pinnacle of mechanical clock making, just before electronic timekeeping came along and made the old technology obsolete. What I want to know is this: how good is it? How does it measure up to what we use today? Fortunately, I've got just the thing to help me find out. The fourth most useful thing ever invented, a nylon cable tie. Because I'm going to use this cable tie to position a timing gate below this pendulum. It connects to the Vernier LabQuest just like this and is ready to use. We're going to select pendulum mode and set it up to take data indefinitely. Press OK, press the start button, and now we wait. About an hour and some 4,000 measurements later, we can see that the pendulum period is quite steady and has an average of 0.877156 seconds. Now that means in 24 hours it'll be off by no more than 3 seconds. That's nearly as good as an electronic quartz clock. Very impressive for an old contraption made of brass and wood. That means that the bob of that pendulum is within 0.02 of a millimeter of its optimal position.
Ach du liebe Zeit.
Now, a nice clean average like that might give you a comforting feeling of certainty, but it usually conceals a much more complex and more interesting reality. So let's take a closer look at that data and be prepared to discover something amazing.
The moment we zoom in, we see that the period of the pendulum isn't constant at all. It's constantly changing. A fast Fourier transform reveals that it has some pattern to it, the longest wavelength being a 32-second cycle, corresponding to one complete revolution of the escape wheel. The next features in the Fourier transform are a 4.5-second cycle and its higher harmonics, suggesting that it's going to be a fairly asymmetrical waveform.
And that's exactly what we see. When the escapement kicks the pendulum just right, it sends it out on a larger swing with a longer period, which slowly decays until conditions are just right again, and the escapement kicks it again. On average, this happens about every 4.5 seconds, or about every 5 swings, give or take. And as the escape wheel goes through a complete rotation, a tiny amount of runout or off-centeredness in it makes it work slightly different during some parts of the 32-second cycle than in others. But here's the big question. If you knew every last detail about this clock, and if you knew the period of every swing of the pendulum right up until now, is it possible to predict what the exact length of the next period will be, and the one after that, and every period after that? You might be saying, well, who cares about some clock? All right then, what about predicting the weather more than a few days in advance? Would that be useful? Or how about predicting what the stock market is going to do next? If we can't make accurate predictions about one simple pendulum clock, then how can we imagine tackling those other more complex problems?
You see, Newton's laws of classical motion appear to be completely deterministic. That means that if you know the state of the system right now, you should, in theory, be able to calculate everything that's going to happen later in the future. And people made a big deal out of this determinism, only it turns out to be completely wrong. Because if you have a completely classical system that contains no random elements, no stochastic processes, nothing like quantum mechanics or anything weird like that, if that completely classical system contains even a little bit of complexity, then it can behave in a way that isn't quite random, but that isn't predictable either. That's right, we've now entered the realm of chaos theory.
This is a phase diagram of a computer simulation of a double pendulum obeying totally deterministic Newtonian laws, without any friction or noise, measurement uncertainty, stochastic perturbation, or anything contributing to randomness or unpredictability. Yet, it exhibits chaotic behavior, and long-term detailed predictions about it are meaningless. Let's make a phase diagram of this clock and see if it exhibits any chaotic behavior. A quick and easy way to do this, valid for discrete time systems, is to plot each period of the pendulum on one axis with the one immediately preceding it on the other axis. Then, if knowing the exact period of one swing helps you predict the next one, it should show up on the plot as a fixed path that it always follows. Here's that plot. It's almost as though the pendulum is trying to get to one state of perfect stability that it can never quite reach, because that perfect state keeps slipping out of the way. It defies any attempt to make accurate long-term predictions.
Now if I said, hold on. Much better. Now if I set this clock and let it run for a week, I know that I'll have to adjust the time on it by no more than a few minutes. That much I can predict, but to predict the period of any one swing of the pendulum, never mind the period of every swing thereafter, is virtually impossible to do. It's a subject of mathematical proof now that there are certain calculations that would take a computer larger than the universe, longer than the age of the universe, to get a perfect result. But the problem with Newtonian determinism isn't just that it's impractical. Like most philosophical debates, the debate about determinism was about something that never even existed in the first place. You know, that's why you can never know for sure what the weather's going to be like on any given day next year. That's why the stock market does what it does. I think it's incredible that a humble pendulum clock like this could outwit some of the greatest minds in science. What's even more amazing is how much you can learn from a simple thing like a clock. What do you think, Einie? He's a genius. but a bit unpredictable at times.
Because I'm going to use this cable tie to position a veneer photogate under this pendulum.